In this first example, we'll talk about a circuit with a capacitor. We're interested here in the voltage across the terminals of the capacitor, and the input is a pulse, like that, when the duration of the pulse is just 1 second in this case, and the magnitude of the voltage during that second is 12 volts. So what we can do is we can separate this in two parts. From 0 to 1, the input is constant and is 12 volts, and then from 1 to infinity it's 0. So we're going to start first by taking a look at the circuit when the time goes from 0 to 1. During that time, the input voltage is constant, and in this example is 12. So from 0 to 1, you have a constant voltage of 12 volts. Okay, what's going to happen here is the capacitor is going to start charging. So this is the circuit that we have from 0 to 1. What we have here is basically the same circuit as before, but now the input is just a constant source voltage, providing a voltage of 12 volts. And we have to find the voltage across the terminals of the capacitor. And we know we can find that voltage in terms of an equation. And we know that equation is given by K1 plus K2 times e to the minus t over tau. So our task now is to find K1, K2, and tau using the circuit that is valid from 0 to 1. So how do we find K1? Well, K1 is the steady state value of the voltage across the capacitor. Steady state value of Vz. So what do? Well, we have to draw the circuit under steady state conditions and find the volts across the terminals of the capacitor. So what we do is redraw the circuit, but now we replace the capacitor by an open circuit because that's its behavior under steady state conditions. And now we have to find the voltage between the terminals of C, and that is the value of K1 we're looking for. Just one loop here, and we need to find this voltage that corresponds to the voltage across the 2K resistor. So we can't just apply a voltage divider here, and we get 8 volts. So 8 volts are being dropped across 2K, and that's exactly the same voltage K1 we're looking for. That's the voltage across C under steady state conditions. Now how do we find K2? The constant K2, we have to take a look at the initial conditions here. At the beginning, we are assuming that the capacitor is fully discharged. So that basically means that its voltage is 0. So to find K2, let's look at the initial condition. What we have here is at t equals 0, the voltage Vc is 0. So V naught of 0 is 0 as well. So what we do is we take the expression for the voltage and we evaluate that at t equals 0. So we take this equation here, but we evaluate at t equals 0. And this whole thing has to be equal to 0 because that's the initial condition. So from here we get the exponential e to the 0 is 1. So at the end what we get is K2 is minus K1. We already know K1 is 8 volts, so K2 is just minus 8 volts. And we're done with K2. So K1 is the steady state value, and K2, we have to take a look at the initial condition. In this case, 0. How do we find tau? Well, it's just R Thevenin times the capacitance. Considering we can find R Thevenin considering the capacitor as the load. So I have to go back to the circuit that is valid from 0 to 1. Replace sources. In this case, the voltage source we replace it with a short circuit. And then we find R equivalent with respect to the capacitor. Here we have to find R Thevenin. In this case, it's just 1K in parallel with 2K. And we get 0.66K. With this R Thevenin, we can find now tau is just 0.66 milliseconds. 0.66 times 10 to the minus 3 seconds. So now we have everything. We have tau, k1 and k2, and we can write the whole expression for the voltage v naught of t from time 0 to 1. So we have k1, k2 and tau, and we can write the whole expression as this. So from 0 to 1, the voltage is going to go from 0 and it will reach a particular value, but this is the equation that is valid for the voltage. Now, what happens for time t greater than 1? Well, the input voltage is just 0. So we can redraw the circuit for t greater than 1, exactly the same as before, but now the input is 0. So what we do is we take the same circuit here, but now the input is just 0 volts. So we can express that like this. We have the input here providing 0 volts, and then 2 resistors, 2K, 1K, and there we have the capacitor. And now we're looking for the voltage here, V naught of t, for any time t greater than 1. Now we have a voltage source with 0 volts. Just to avoid confusion, this is exactly the same as if we put here a short circuit. There's no voltage drop. And now we can work with this. As you can see here, the capacitor is now discharging through both resistors. And the expression for the voltage is the same as before, but now we have different constants. Now C is going to discharge through 1K and 2K for any t greater than 1. Now this expression that we get here should be valid for t greater than 1. This is where the capacitor starts discharging, so we have to include a time shift in the expression, otherwise it's not going to be valid for, or it's not going to start at t equal 1, it's going to start at t equal 0. We have to make a time shift, move this whole thing 1 second to the future, so that it starts at t equal 1. So we have to change the argument and put t minus 1. And we have to find out constant k1 prime, k2 prime, and tau. Tau remains the same because it is exactly the same circuit we used before to find our Thevenin. So tau is exactly the same. It's going to be 0.66 times 10 to the minus 3 seconds. K1, same as before, is now the steady state value of the voltage, but we have to use this new circuit. The capacitor is now fully discharging. It's going to fully discharge for a sufficiently large t. Eventually, all its energy is going to be gone. So that basically means it's going to discharge completely. So what is the steady state value under this condition? It's just 0. There will be no voltage across its terminals. So K1 prime is 0 because the voltage between the terminals of C will reach 0 eventually. So the steady state is just 0. There will be no energy stored in the capacitors. It all will be dissipated by the resistors. How do we find K2? Well, let's look at the initial condition. From 0 to 1, from time 0 to 1, the capacitor was charging, and the maximum value of the voltage is given by the expression we got before. So we have to go back and use this expression here. This was the equation that was telling us how the capacitor was charging. If we evaluate this expression at t equal 1, we're going to get the maximum value of the voltage the capacitor was charging. And in this case, if we evaluate this at t equal 1, we're going to get 8 volts. At that point, the source switched to 0 volts, and the capacitor started discharging. So the initial condition is 8 volts. Now we have to take this equation here and evaluate at t equal 1. We have k1 prime, k2 prime, e to the minus 1 over tau. 1 minus 1 is 0, e to the 0 is just 1, k1 prime, we already know this value is 0, and the exponential is 1. So at the end we have k2 prime is just 8 volts. That's the initial condition. So that capacitor is going to start discharging with an initial value of 8 volts. It will eventually reach 0 volts. So we have the whole expression here. K1 prime is 0, K2 prime is 8, and tau is 0.66 times 10 to the minus 3. And that's it. If we want to plot this equation, what we have here is from 0 to 1, the capacitor is charging. That's when the input is 12 volts. That's the equation that is valid from 0 to 1. So it's going to start at 0 and is going to eventually reach 8 volts. T equal 1 is approximately 8 volts. And then the input voltage goes to 0, and now the expression for the voltage V naught of t is the other one. That's the discharge phase, and is going to reach 0 volts there. In this new example, now we have an inductor, and we're looking here for the current. Now we're looking for the current flowing through the inductor. At t equals 0, we close the switch, and we're going to have current flowing through L due to the current source and due to the voltage source, and we want to find that current. Similarly, as the case of capacitors, for inductors, we have to use basically the same equation for the transient response. But now tau is we calculate tau with inductance divided by R Thevenin. But the meaning of K1 and K2 is the same. You just need to calculate tau differently. K1, steady state value of the current. So we basically have to again redraw the circuit under steady state conditions, and that means we have to replace the inductor with a short circuit and find the current. So we put the 1 amp source, resistor here, resistor there, the sources, and then we have here under steady state conditions the inductor is just a short circuit, and we are looking for the current there, and that's the value of K1. We're going to have a current here due to the current source and due to the voltage source. You can apply superposition or any other technique to find that current. I'm going to use loops here because it seems to me that it's very simple using loops. We have two currents, I1 and I2. We already know I1 because of the current source is 1 amp, and I2, we have here just 1 volt being dropped across the 10 ohm resistor, so this is just 1 over 10.1 amps. Now the inductor is right in the middle here. Both currents I1 and I2 are flowing downward, so we can find IL by adding them up, and we get 1.1 amps. That's the steady state value of the current. Now for K2, we have to take a look at the initial condition. In this case, at t equals 0, that's the moment when we close the switch. So at that moment, the current is 0. So at t equals 0, there's no current flowing through the inductor, and because that's the moment when we close the switch, there's no current at the beginning. So what we do is 0 has to be equal to the expression of the current evaluated at t equals 0. It's K1 plus K2 e to the minus t, in this case t is 0, so the exponential is 1. And this is the same condition we have every time the initial condition is 0. K2 equals minus K1. K1 is 1.1 amps. So K2 is minus 1.1 amp. And finally tau. For tau we need to find R Thevenin. Now considering the inductor as the load, so we have to go back to the original circuit and Replace current source with open circuit, replace voltage source with a short circuit, and find our equivalent between the terminals of the inductor. So here's the inductor. There we have the short circuit here instead of the voltage source. And we have to find R-Thevenin between those two terminals. The 1 ohm resistor is disconnected here, it's open, so the only resistor contributing to R-Thevenin is just 10 ohms. So that's R-Thevenin. So tau is going to be the inductance, 1 millihenry, divided by R-Thevenin, that is 10, so we get 0.1 seconds. 0.1 milliseconds. 0.1 times 10 to the minus 3. So we have everything now. The expression for the current is 1.1 times 1 minus e to the minus t over tau, 0.1 times 10 to the minus 3. And we can plot this equation. That's the equation for the current is going to start at 0, and it's going to increase exponentially until it reaches a final value of 1.1. That's the steady state value of the current. So it starts at 0, increases exponentially until it reaches 1.1.